The first concept is the finite element method introduction of the lecture. So you have some basic knowledge, and then also you can step by step to know or to understand this lecture. First, some concept. The first concept is the finite element method. So what is the finite element method, and why is it used a lot? So the finite element method is a numeric method. So let's have a look at the example here. So we have an object. This is an object. It's a solid object. So the finite element method is to solve these problems. The finite element method firstly discretize this object into many small elements as shown here, and then they solve the equations for each element, and then assembling them together, and then solve the whole system. So this is the finite element method. So the basic and the important idea is to discretize the systems, and then to solve them, assembling them, and then to solve the equations. So we will talk more details about this procedure. And then the element, the concept or the definition for the element, also for the nodes. What is the element? The element is the minimum cell or the minimum part after the discretization. And what is the node? The node is the connection point between elements. That's the node. For example, here we have the discretized object, and we have those triangle, and those triangle, they are the elements, and the between the triangle is the point, and we call this the nodes, the element nodes. So this is the node. So for this system, if we give a force, and then the force will pass through all the nodes and the elements, and then into some other part of this object or other part of these systems. So this is the definition for the nodes and for the elements. So you should know if we increase the number of the elements, because you may notice the problem here. So this edge, this curved line is the actual geometry of the object. But when we use the finite element method, we use the triangular to match the object, and then so there's some kind of discrepancy, some kind of the error or the discrepancy between the actual geometry and the element, the matched element. So how do we reduce this discrepancy? We can do this by make our element smaller, and that is to increase the number of elements. Then the actual geometry and the matched geometry, they can match with each other, and when they are matched, the error introduced by the finite element analysis will be minimal. So we are talking more about this. So it's important that you know this, so when you do the analysis, you don't make mistake, or you can correctly understand your problems or understand your analysis. Second, let's talk about the development of the finite element method, or the history of this method. So this method, so in 1943, some people they tried to use several triangles to solve a continuum problems. Some scholar, some researcher, and then in 1956 there was some annual meeting of aerospace, and so in this annual meeting, some other scholar they proposed a new idea, that is to partition the structure into triangular and rectangular, and then form the stiffness matrix. And this is the beginning of the finite element method. And in 1960, the world finite element was first proposed in the book, The Finite Element Analysis in Plane Stress Analysis. And then eight years after, the mathematician recognized the advantage of the finite element method, and then they developed the method into a new height, which means they improved method. And then in the 17th, the first nonlinear FE software Mark is appeared. And 5 years after, another software solver, Adina, emerged, which means it appeared. And 2 years later, the mechanic dynamic developed. They developed the Adams, and this software is mainly used in the mechanic kinematics in the dynamic simulation. And in 1978, so please remember this year, the Abacus was released. The Abacus is the most widely used FE software nowadays. So, and then some other dates, the 1988, Astana was released. Astana is also widely used, but compared to Abacus, Astana is mainly used for the crash simulation. Some people know in the car industry, the Astana is widely used and is mainly for the car crash simulation. But nowadays, it's also used in some other dynamic scenarios for the simulation of the dynamic scenarios. In 1996, another major software, ANSYS, is released. ANSYS and Abacus are two main software in the FE analysis nowadays in different field, and they are Abacus and ANSYS. They are compatible, and they compete with each other. And then nowadays the ANSYS they reduced some new package, like the ANSYS mechanic is mainly for the mechanic analysis. The ANSYS CFD, this is for the CFD analysis, and the ANSYS workbench, which is integrate different software together. So we have so many different softwares. So no matter which one it is, all the FE software, they include the three modules: the preprocessor, which means in the preprocessor, we create the model, we define the material, we define the element, we define the boundary condition, etc. Then the main part or the king part is the solver, which means we solve the nonlinear equations, we solve the FE stiffness equations, and then we do the post-processing. So in the post-processing, we plot the stress, we plot the strain, also we plot the strain energy density and all other parameters. This is the one example of the ANSYS menu, ANSYS interface. So we have different parts. So we have the menu, we have those are the main menus. The preprocessor, you can see mainly three parts: preprocessor solution, the post-processing, and we have here is the status, and those are for the review. And here there's some FE application, the examples. So the finite element analysis is used in different fields to solve the problems. The first is the medical field. So we use the FE to predict the outcome of the surgery. And the second is in the aerospace. So we simulate the rockets, the flying of the rockets. And the third is in the mechanics, in the mechanical engineering. So we simulate the rolling of those steel. And the third is in a train. The fourth is in a train industry. So we simulate the crash of the train cargo. here is at least some typical element types. So we will give more details in the subsequent lectures. So here we just give you an overview. The first type is the bar element. Second is the beam element, the plane triangular element, the plane rectangular element, the shear element, and tetrahedral element. So we will, in the subsequent lectures, we will give much more details on each of the elements, how the software analysis those elements and how they get the solutions, and when we do our own analysis, which element should we pick, should we use, and if you pick the wrong element, you'll get the wrong results. That's why you need to know the physics, the background. You need to know the theoretical calculation process. Okay, so now part 2, some basics of the elastic mechanics. So this is also some review of the previous knowledge. So if you don't understand what I'm talking about, or if you don't know those basics, I suggest to find some books and then to read through the books to understand those basics. Once you know those basics, and much easier for you to understand this lecture, to understand this course. So first, we have some fundamental assumptions in this in the finite element analysis. Here, we talk about 4 fundamental assumptions. The first one is the continuum assumption, which means the matter in the body is continuously distributed and fills the entire region of the space it occupies. Advantage of this assumption is, due to this assumption, the physical measure, for example, the strain and the stress, are continuous. Therefore, we can use the continuous function to express the problems. And also there's a note, the continuum assumption is only used in the micro scale. So in a very small scale or nanoscale, normally you don't have the continuum assumption, because we know in the nano or even smaller scale, the material is made from the atoms, and is the interaction of the atoms that produce the force and transmit the force. So it's different. We have to use different theory to solve those equations. And then the second assumption we made for the theory we talk about. This is to reduce the complexity of the problems. So we make the second assumption, which is the linear elastic assumption. So this is the stress strain curve we all know very well. So this is the curve for the matter, the steel. So we have the elastic region, and then we have the yield point, then we have the plastic region, and then we have the fracture, then we have the fracture. So for the matter, the elastic region is linear, and for some other material like the rubber or like the soft tissue, the elastic region is non-linear. So in order to make the problem easier, so we assume all the material we analysis is the linear elastic material. So the equations can be much simpler for us to understand. So the advantage of use the linear elastic assumption is the stress-strain relationship is linear, and the material elastic parameters are constant. The third assumption we make is the isotropic and homogeneous. So we assume the object is made of one material, and there are the same mechanical behavior in any part and any direction of the object. So the advantage of this assumption is we can take any part of the object as the representative volume. So So the isotropic homogeneous material is the simplest case for the analysis. So in a real situation, we have much complex material. For example, we will have the heterogeneous material, which means the material is a mix of several different material. As we see here, different color represent different material, and so those are very important concepts: homogeneous, heterogeneous, isotropic, orthotropic, anisotropic. So if you don't know those definitions, you should really check check online or material or read some books, relevant books, to understand all those concepts. So we don't talk too much about those because in this lecture we talk about the finite element analysis. Those should be the knowledge from the material engineering science. So here example is more complicated than the isotropic material. Is the orthotropic material. So the orthotropic material, it has at least two orthogonal plane of symmetry, and the material properties are different and independent in the x, y, and z directions, and it requires 9 independent elastic constants. So why it has 9 independent elastic constants? Why it has two orthogonal plane of symmetry? And you have to understand by yourself, and why the stiffness matrix is in this form. So you have to understand after the lecture. So one example of this material is the wood. Is the wood. The wood, we can see we have many rings. And they have two orthogonal plane. So one, for example, one orthogonal, the symmetric plane is this plane, right? If you do a mirror, so they have they can mirror back. So this is the symmetric plane. And another type of material is the transverse isotropic material. This material is also very common and is widely used in the engineering problems. For example, we have those, and we have this object composed of two parts for the matrix and the fibers. So a real example of this material is the skeletal muscle. We all have the muscle. For the muscle, we have the fibers, and we have the basic matrix. So it's a typical transverse isotropic material. So which means the mechanical property along the fiber direction, in this direction, will be stronger in the transverse plane or in the transverse direction. And in the transverse plane, the mechanical property is the same in different directions. So we see the transverse isotropic material is a special orthotropic material, and there are different examples. We already talked about the skeletal muscle. Another example is a polymer reinforced by the parallel glass or by the parallel fibers. The most complicated material is the anisotropic material. The anisotropic material requires 21 elastic constants, and you can find more details about this material in this website. The last assumption is the small deformation assumption. So, which means the displacement and the deformation is small and much less than its dimension. So, second sentence is important. We say small deformation is comparable. It should be comparable to its dimension, because if you have a very, very small object, for example, if you have a 1 millimeter object, the length is 1 millimeter, then the displacement of 0.5 millimeter will be large. If you have a 1 meter object, then the same deformation 0.5 millimeter will be very, very small. So it's a relative, should be relative to its dimension, and it should be much less than its dimension. So the advantage of use when we make this assumption is we can ignore the object dimension change caused by the deformation, and ignore the high order part, and simplify the equation as a linear elastic equations. So which means we can really simplify the problems. So we make all those 4 assumptions to help us simplify the problems. So then we can talk about the solution procedure for different elements, for the bar, for the beam, for the triangular, for the rectangular elements. But in the real engineering problems, always you have the nonlinear property, you have the large deformation, you have the anisotropic material, and in those cases, you should ignore those 4 assumptions. So the reason we make this assumption is only in order for you to understand the analysis procedure, and it's only for this aim. So don't be confused or don't be mixed up. Don't say this assumption is for every engineering problems. It's not. It's only for introduce the theories. Otherwise, the equations are too complicated, too complex. Now some other mathematic basics. First is the tensor operation, the tensor opposition, the index notation, and the tensor notation. So with the wide variety of variables, elasticity formulation makes use of a tensor formalized using the index notation. This enables efficient representation of all variables and Gaussian equations using a single standardized method. So the index notation is a shorthand scheme where a whole set of numbers or components can be represented by a single symbol with subscript. This is the definition of the index notation. And then index notation also used a lot in different textbooks, in different books, in different papers, or in different publications. So you really very important basic knowledge. If you know this, and then you can understand what they are written in the books or in the papers and in different material. So we give an example here. The zero-order tensor is the scalar. For example, the string energy. For example, the body weight, the body height. It's a scalar, zero-order tensor. The first-order tensor is the vector. For example, the displacement. For example, the direction vector, the direction of the direction vector. The direction vector. So it's one-order tensor. It has one free index, and the second-order tensor is a tensor with two free index. For example, the stress and the strain. Okay, so the scalar is with zero free index, the vector is one free index, and the tensor is two free index, second-order tensor. And the index notation. This is also a very important part. So we have the free index. For example, the sigma, the stress, sigma ij. So here we have two index. So it's a second-order tensor. And here I and j, both I and j, they are free index. And we have another very important definition, the dumb index. So for example, in this equation, we have aij xj equals bi. So here, I is the free index, but j is the dumb index. So j is the dumb index. So why j is the dumb index? Because in one term, so aij times xj is one term, bi is another term. So we have two terms here. So in one term here, in the first term, we have the we have the index appeared twice. We have the index j appeared twice, and that's why it is the dummy index. If it appears twice in the term, then it's the dummy index. So we have the definition here. If a subscript appears twice in the same term, then the summation over, which means we should do the summation over that subscript from 1 to 3. For example, here, of course, it depends on how you define the range for the dummy index. If it's defined from 1 to 3, then you do the summation from 1 to 3. If you define its range is from 1 to 5, then you should do a summation from 1 to 5. Okay. So give an example here. AII here, the index appeared twice in the same term, so we do the summation of I from 1 to 3. So which means AII equals to A11 plus A22 plus A33. Okay, so this is the definition of AII. And the second example, AIJ BJ. So here, with the index j appeared twice in this term. So which means we should do the summation of j for this term. So we do equals to aij bj, and then j equals to 1 to 3. Then we do the summation. So we keep I the same. So which means equals to ai1 b1 plus aij b2 a plus ai3 b3. So which means we do the summation of the index of the dummy index j from 1 to 3. Okay, so this is so always people when they do the writing, they write as this AII for this equation they write aij bj. Okay, so we can also write those terms, but it takes more time for your writing, and it looks more complex. So people use the index notation to simplify the writing. Also, they make the writing more efficient and they make the writing quickly. So here we have the equation. The becomes more complex. We have those equation. We have those equation, and we want to simplify these equations as the index notation. So we have the let's have a look. We have three equations. And for the first equation, we have 1, 2, 3, 4 terms, and also we have 4 terms in the second equation. The 4 terms in the third equation. We can see there are some rules here, or some we can see B1, B2, B3. So it's it's a loop from 1 to 3, and then here we see x1, x2, x3, right? And here is A11, A12, A13. And if we look in this direction, we see A11, A21, A31. Okay, so it's clearly there are some iterations here. So in order to write out the index notation, we have to understand what is the free index, what is the dummy index. So we said if we do the summation, and then which means there might be the dummy index. If we don't do the summation, if they appear in different equations, then it is a free index. So which means here B11, B1, B2, B3, they are in 3 individual equations, which means the index for the B should be a free index. So that's why we have the BI. And here is the same. We see in this direction, we see A11, A21, A31. So the iteration 1, 2, 3 in different equations. So here it's also AI. I is a free index. So, but if we look at the same equation, we say x1, x2, x3, and which means they are doing the summation. So which means the index for the x variable is a dummy index. So we have the xj, the dummy index, which means we need another another j in the same term. So we say a11, a12, a13. So the second number is also doing the summation. So we can write aij xj. Here the j is the dummy index, and we have the I is the free index. So in short, we can ignore or we can skip those summation symbols. So we can write as aij xj equals to bi, and people when they read this, they know, okay, j is the dummy index and I is the free index. Okay. Now we talk about the kinematic rules. This is a rule to simplify the matrix. To simplify the matrix is a rule to convert the high order tensor into the low order tensor. So for example, if we have a stress sigma ij is a second order tensor because it has two index, two free index. So if we write out if I and j they equals to 1 and 2, then we have this 2 times 2 matrix. So we can use the kinematic rule to convert this second order tensor into the lower order tensor, which means into the first order tensor. So because we all know for the stress is a symmetric matrix. It's a symmetric matrix. Because it's symmetric matrix, so we don't need sigma 1 2 and sigma 2 1, which means sigma 1 2 equal to sigma 2 1. So we only need one of them. That is enough. That's why we can use the kinematic rule. So we use the kinematic rule. We only take the diagonal elements sigma 1 1, sigma 2 2, and then we take one of those value in the non-diagonal position. So we take sigma 1 1 2. So we don't need sigma 2 1. So which means we can simplify it as sigma 1 1, sigma 2 2, sigma 1 2. So then this is a one order tensor. So which means we have managed to convert this second order tensor into the first order tensor. So we have simplified the expression for the stress. So here is I and j equals to 1 and 2. So it's two-dimensional problems. So for the three-dimensional problems, we have the 3 times 3 matrix for the stress, and we can also we apply the kinematic rules. So we can simplify the stress tensor as a one order tensor, and it has 6 elements or 6 components. And we can do the similar to the string. And once we have do the simplification for both string we convert the stress to the force. So we do the we times the area. So this is dy is the length and t is the thickness. So we convert by times the area. We convert it into the force, and it's along the negative direction of x. That's why we have the minus. Okay, and then we have this force is along the x direction. So this force. This is along the positive x direction. So we it's positive. It's a plus, and this is the stress. And what's the area? The area is again is dy. This is dy times the t times t. Okay, then we have this shear stress, right? This shear stress is along the x direction. So this shear stress that is along the positive direction of x. That's why we have the plus. And how about the area? This shear stress is in this area. So this area, the area of this surface is dx. So this is dx times the t. Okay, and then we have this shear stress. This shear stress. This is also in the negative direction of x. So we have the minus. Then we have the body force. Then we have the body force. So then we have the body force. Then we sum all of them together. They should equals to 0. So we have then we have the first equilibrium equation. So all the forces in the x direction should be 0. And then if we do the mathematics, we get this equation. And this is a very important equation. Is set up the relationship between the stress and between the normal stress, shear stress, and the body force. Okay, so similarly we can do use the condition all the force in the y direction should be 0. Then we get the second equilibrium equation, and then we have take use of the third condition. All the moment at any point will be equals to 0. Then we have the third equation, and then after we do the mathematics, we get this form, and this is which means the shear stress the shear stress equal. Okay, so in summary, the equilibrium equation for the 2D problems is those three equations. We should be very familiar with those equations. Okay, all right. So this is a very important equations, and its basis for solve the finite element method for the finite element analysis. And this equation for the 3D problems. We have those equations here. So we know this equation. This is when we do the writing, it's complicated to write those. So we can take use of the index notation. We can write those three equations into the index format. Now we can also say which is the free index, which is the dummy index. Once we notice which is the free index, which is the dummy index, then it's easier to write out the index format. So we said if it appears, if we do the iteration or do the loop in different equations, then it is the free index. If it's doing the summation in the same equation, then it is the dummy index. So let's look f. We have fx, fy, fz. So we can say this is doing the iteration in different equations. So the index for f should be a free index. This is a free index. So now let's have a look in one equation. We have the partial x, partial y, partial z. So this is which means we are doing the summation. So which means here the index for this parameter should be a dummy index. And here we have a look. We have the tau sigma xx. We can write as sigma xx. Okay, tau yx we can also write as sigma yx. So we can say xx, yx, zx. So which means the first parameter is doing the summation in the same equation. So we write as so we notice this is a dummy index. This is a dummy index. That's why we write sigma I, j, and I. So the first letter is the dummy index, and we take the partial derivative to the dummy index. Okay, and the second one, the second letter, x, y, z. So we can say it's doing the iteration in different equations. So it is the free index. J is the free index. Okay, so this is important, very important. If you don't know how to do those, how to convert those equations into the index format, you should do more examples. You should do more practice after lecture. And the second is the stress and the displacement relationship. Here we take look at the 2D case. So we have an object. We have the object A, P, and B, and it's deformed. This is the deformed shape. It's A bar, P bar, and B bar. And for this, we say the coordinate for the P is X and Y. And the coordinate for A is x plus dx and y. Coordinate for B is x and y plus dy. Okay, and so for the point P, it's deformed, and the displacement is u and v. So we say here the xy displacement at point P is u and v, and we represent u and v as a function of the coordinates, which means as a function of x, y, and z. So then we can work out the displacement for the A point for A, and we can also work out the displacement for B. Okay, let's have a look how this is done. So once we know the displacement at P, and then we can see the displacement at A and B. So we said the displacement is a function of the coordinates. So which means if we want to know the displacement for A and B, we just put the coordinates into the function. So this is for point A. So point A, it has the x coordinate is x plus dx. Okay, y is the same as p, z is same as p. So then we put into the u displacement u function, then we get the displacement for point A. Then the y direction displacement for point A is VA. Again we put the displacement of coordinate of A into the function, into the V function. Okay, then we get the x direction displacement and the y direction displacement for A. And then similarly we get the displacement for B, the displacement for B. So we have the U. So the B, for the B, it has the displacement, the coordinate x, and the y coordinate is y plus dy. So we put those into the function. We put the coordinate of B into the function, then we work out the x direction displacement and y direction displacement for point B. And then we do the Taylor expansion. We can simplify. We can ignore the high water part. Then we only take the first part and the linear part. So we have the displacement for A. This is the x direction, and this is the y direction. And also we have the displacement for B, x direction and y direction. And we have written here. So this is the displacement for A, This is the y direction displacement for A. This is the x displacement for B, and this is the y direction displacement for B. Okay, so now you understand all those, and I have talked through how we get those, and it's from the Taylor expansion. And okay, so now this should be easy to understand. And then let's talk about the elongation. So what is elongation? Elongation we define as the change in the displacement times the original length. So for example, the elongation along x direction we represent as sigma, as epsilon xx. So then it's the change in the length. So which means it's the here we have the change in the length. So this is the length time divided by u, and then it's the initial. Okay, then the initial length of AP is dx. Okay, then one step is skipped here. So the initial length of is u. Okay, u should be u plus, is u plus this distance. Okay, this is the PA, and then the deformed length of PA of P bar A bar is this plus the same. If we delta the same. Okay, so the initial length of PA is u times delta. The deformed length of PA is this one plus delta. And then we do the minus, we do the subtract, and then we have eliminate those, and then we get this, and then we do the mathematical again further, then we get those. So which means the relative elongation along x direction, epsilon xx equals to partial u partial x. Okay, so similarly we can work out the relative elongation along the y direction, so which means epsilon yy should be equals to what? To p bar b bar, the length of p bar b bar, minus pb divided by the length of pb. Okay, so this is the definition for the string. This is nothing but the definition for the string. So then we work out the length of pb. Length of pb is dy. Okay, dy, and then pb here is equals to, if we represent this as delta, so this is u plus delta. And how about p bar b bar is this value, right? Is v plus partial v partial y dy plus delta. Okay, and then times pb. Okay, then we do the further mathematics. We can work out epsilon yy equals to partial v partial y. Okay, so this is the definition for the string. That is the relative elongation along different direction. Then we define the angle change. The angle change is the shear strain at for example, the angle change at point P. So first the tangent alpha, because we said we make the assumption of small deformation, so which means tangent alpha approximately equal to alpha tangent beta approximately equal to tangent beta, because the assumption of small deformation. Okay, so the tangent alpha equals to, we have the alpha. Okay, the alpha is here. This is alpha. So the tangent alpha equals to this distance, right? This distance equals to this one minus this one, right? And divided by dx, okay, divided by this, okay, this is the tangent alpha. If we do the mathematics, it's partial v partial x. And then the tangent beta, this is our beta. The tangent beta is this value. This value equals to this one minus this one, and then divided by the initial length, dy. Initial length is dy, okay. And then this is a tangent beta, approximately equal to beta, okay. Then the angle change at this point is equal to the change of is the sum of alpha and beta. So gamma alpha xy equals to alpha plus beta and equals to this one. So this is from here we get the, so this is actually is the string and the displacement relationship, because here we have the displacement and here we have the string, okay. So we do a sum up for the string and the displacement relationship. We have the string in x direction, we have the string in the y direction, we have the change in the angle, so it's a shear string. So we have we have three equations. We can simplify it as the index notation. We can simplify it as the index notation to represent the three equations. So when we talk about the string and displacement relation, we talk about compatibility condition. So what is the compatibility condition? So let's have a look at the example. So this is the undeformed. This is undeformed. This is undeformed, and these three are the deformed. We can see there's problems here because this is a continuum. We have made the assumption continuum. This is a continuum object, but in case 1 and case 2, the continuum becomes not continuous anymore because there's gap here and there's overlap region here. So this is obligate to our continuum assumption. Only case 3, the deformed shape is still continuum. So in order to avoid occurrence of case 1 and case 2, we have to introduce the compatibility condition. We have to introduce the compatibility condition to avoid those two cases. So what is compatibility condition? This is the reason why we introduce compatibility condition. So then what is compatibility condition is we set up additional equations. We set up additional equations and we set up higher order equations in order to make the string at the interface compatible, which means they will not separate from each other or they will not overlap with each other. Okay, this is the compatibility condition. You can read more material on this from other books. And then we have the summary of the stress and strain relation for the 3D case. So we have 6 stress and strain relation equations for the 3D case. And then this is also called the geometry equation or the Cauchy equation. And here we know if the displacement UVW represents the displacement in the x, y, and z direction. If those are known, then the strain can be determined at any point. So inversely, if those strings are known, the displacement UVW cannot be determined. Why? Because there's the rigid movement. Because there's a rigid movement. We will talk more about what is rigid movement. And which means once we know the string, if we want to work out the displacement, we have to provide additional boundary conditions. Only the additional boundary condition is provided, then we can work out the string from the displacement. And this is the third type is equation is the stress and the strain relationship, which means they define the relationship between the stress and the strain. And in those definitions, there are several important mechanical parameters. For example, E is the elastic modulus, G is the bulk modulus, and mu is the Poisson ratio. And there's a relationship between different parameters. And the stress-strain relationship also can be written in the matrix format. And in the matrix format here, D is the elastic matrix, or sometimes we call it the stiffness matrix. And here there's another parameter lambda, and G is the definition and what's the format it is appeared in the matrix. And the final part of this lecture, we will talk about the boundary conditions. There are two types of boundary condition. First, the displacement boundary condition, so which means we know the displacement at certain boundaries. So, for example, on this surface, we know the displacement U equals to U bar, and V equals to V bar. Now we have the force boundary condition. So which means this is the object, and at the certain region, we know the force. At those region, we know the force, and we can set up, because we said we are dealing with the static problems, so we can set up the equations to link the forces by using the equilibrium equation. So, which means all the force in the x direction equals to 0, and all the force in the y direction also equals to 0. Then we can establish the relationship between the internal stress sigma tau, between the internal stress component and the external force px and py. So then we can solve. Once we know the external force, then we can work out the internal stress at the specific point. Okay, so we finish here, and now let's continue to finish the rest part. So then we have the plane stress problems. So what is the plane stress problems? So under the following condition, the problem can be seen as a plane stress problems. First, it should be a very thin plane, as we show here. It's a very thin plane, and there's a constant force. We see here this arrow means the force. The force are constant and parallel to the plane of the plates, and the force are also constant along the thickness direction of the plate. And for the plane stress problems, there's no external force on the surface perpendicular to the plane of the plate. For example, in the z direction, there's no external force. There's only external force in the x direction, and no force in the z direction, which means because of the equilibrium condition, so any internal force in the z direction, they are equal to 0. So this is one feature for the plane stress problems. So if a real engineering problem can be simplified as the plane stress problems, and then there's only 3 stress components, and stress and strain in the z direction is not necessary to 0. Okay, the stress is 0, but the strain and the displacement is not 0 because there's definition in the z direction. So for the plane stress problems, the equilibrium equation, the strain and displacement equation, the stress and strain relation, and boundary condition, they all can be simplified. They all can be simplified as a 2-dimensional problem. You can try by yourself to simplify all these equations from the 3D case to the 2D case to the plane stress problems case. Another types of 2D problem is the plane strain problems. So what, in which case, under what condition the problem can be treated as plane strain problems? So we have the following conditions. First, a very long cylinder. So this is cylinder very long. It's very long in the z direction. And the second, we have the force, but the force is parallel to the cross section. Okay. And the third, the force is constant along the length direction, which means in the cross section in the z direction, any cross section in the z direction, the force is the same. Okay. And because the cross section is symmetric, and therefore we have the strain. The strain in the z direction equals to 0, and also the shear stress is the associated shear stress is 0. Okay, so and then again, for the plane strain problems, the stress in the z direction is not 0. It's normally not 0 because there's no deformation in the z direction. Okay. And all those equations and relationships, they can be written as the simplified form, in the simplified format, and you can do this as a practice for yourself to reduce the general 3D cases, the 3D equations into the plane strain problems. Okay, so this is the end of lecture 1. So in the next part, in the second lecture, we will talk about the also some very important basics. And so thank you. This is the end of today.